Welcome to this NPTEL lectures on principles and techniques of modern radar systems. So, in last class we have done tutorial 1 on basic concepts. We are continuing that. Actually, what I scheduled earlier, that one such problem left remaining, one important problem. So, that we will see now. You see this fourth problem of the previous tutorial. It is a very interesting problem. Determine the peak power and the antenna physical area which would make the cost of the following radar a minimum. So, frequency is given, antenna aperture efficiency is given, receiver sensitivity is given, unit cost of transmitter is rupees 132 per watt of peak power, unit cost of antenna 80,000 rupees per square meter of physical area, cost of receiver and other cables etc., other items 60 lakhs. Also the radar must detect a non-fluctuating target. What non-fluctuating target means, that later we will see. Let us say that it has a constant RCS of 10 meter square cross section at a range of 200 kilometer by measuring a single echo pulse. So, you will have to find what are the respective cost of the antenna and the transmitter, and then based on that in a new radar design, how you do try as a first attempt to allocate the cost between the antenna and transmitter based on the answers obtained in part C. So, you will have to find, you see, peak power and antenna physical area which would make the cost of the following radar a minimum. Also you find the respective cost of the antenna and the transmitter. So, 4 things need to be found out. Now, apparently it looks like an economic problem, but no, to solve this problem also you need a model. Actually, you see, in anything you need to analyze in engineering, you need a model. So, radar is a system. So, to evaluate its cost also scientifically, you will have to have a model, and that model is nothing but radar range equation. So, you see that very elegantly if we use the radar range equation model. So, I am writing this is problem 4, and so since it is a question of cost, let us say the total cost, I am breaking into 3 parts as suggested by the problem, the cost of transmitter plus cost of antenna plus cost of receiver. Now, it is said that CT, that is 132 rupee into PT, that is said that per each watt. Similarly, for CA it is said 80,000 into area of the antenna, and for CR it is at a fixed cost. So, now let us come to the radar range equation. We know PT is 4, let us relate PT to R max is given. So, let us connect to R max, whole to the power 4, S min, then GT AE sigma. So, you see deliberately I have taken this AE in the receiving antenna portion, because it will be then related to this physical area of the antenna. Now, what are the things, what is now GT is not said in the problem, but area of the problem will come out. So, we know GT can be converted to area, effective area of the antenna by this formula 4 pi AE by sigma square. So, that will do, and also we know what is the connection between effective area or electrical area of the receiving antenna and the physical area. That connection is through the efficiency, which antenna aperture efficiency. So, that I think this we are calling antenna aperture efficiency. This is in all antenna classes this is said. So, A is equal to A, where this is the physical area of the antenna. So, putting all this in this equation will make it more simple in terms of the our required quantities. So, it will be 4 pi, we will see. So, 1 4 pi will come from here. So, 4 pi R max whole to the power 4 S min lambda square by rho A square into sigma. So, this is whole thing, then I am writing it as 1 by A square. Now, you see for the radar this first ratio, that is all are constant terms, because R max is fixed, S min is for a receiver it is fixed, the carrier frequency is fixed, aperture efficiency of the antenna is fixed, RCS of the target is fixed. So, I can now write it as that some constant k by A square, where k is a constant. Okay. So, Pt, that means is inversely proportional to A square. So, we can say that if this is the case, so we can say that C is 132 k by A square, this one I am now writing, plus 80,000 A plus 60 lakhs. Now, if I want to minimize C, so there it is only depends on A, you see. So, with respect to A, I will have to differentiate. That means, to minimize C, dC dA should go to 0, and that gives me A is equal to 264 k by 80,000 whole to the power 1/3. So, lambda is given, we know what is the value of lambda is 0.122 meter. So, k now we can find out. We can evaluate the value of k, because k previously we have that expression, there we now can put, because now this k needs to be found out. So, k is 4 pi into 200 into 10 to the power 3 whole to the power 4 into 0.5 into 10 0.122 square by 0.7 square into 10. So, this will be 0.3057 into 10 to the power 8. So, we have got k, we have got the value of a which is making the cost minimum. So, now one by one we can answer various parts of the question, that what is part A. Part A already we answered that A is so much, what is the physical area. So, now A will be then P t is equal to k by a square, and so it is 0.3057 into 10 to the power 8 by 46.55 whole square. Now, where from A is coming? Actually, first we will have to find A, then we can come here. So, actually better B can be first found. What is B? B is A is equal to 264 into 0.3057 into 10 to the power 8 divided by 80,000 whole to the power 1/3. So, that will be 46.55 meter square. Once we get this A, we can put it here, and so this value will be putting that we will get is 14.11 kilowatt. You see that by data range equation, we are not only getting the what is the transmitter power required, that is 14 kilowatt peak power, and what is the antenna size, physical area 46. So, both are coming. So, it is not an actually economic question, it is a question of correct modeling. Then C can be now easily found. What is C t? So, C t will be, that means transmitter power 132 into 14107.7 or 14.11. So, that will be 18.62 lakhs of Indian rupees. And what is C A? C A will be 80,000 into 46.55. So, it is 37.24 lakhs of INR. Now, this is an interesting thing. Please see, this is not so obvious that an antenna cost 37 lakhs. The transmitter, we think it is a high value, a high power thing, it is having, you see, 14 kilowatt power, but actually the technology wise antenna technology is much sophisticated, that is why its cost is more. So, what is the outcome of these? That actually that is what you said, you always remember these, that what is this ratio typically C A is to C T. Roughly we can say this is 2:1. So, while allocating fund, always you should give more fund for making the antenna, because antennas technology is more sophisticated for in microwave things. So, that is this problem. Then let us come to the other problem. You see, this is also the problem 1 of chapter tutorial 2. A satellite orbiting the earth in a circular orbit at an altitude of 5000 kilometer has a speed of so and so. What is the Doppler frequency shift if the satellite is observed by an UHF radar operating at 450 megahertz lying in the plane of the orbit? just as the satellite appears over the horizon. Given the radius of Earth is so much, you may ignore the effects of refraction by the Earth's atmosphere and reflection from the Earth's surface. The same thing is asked, what is the Doppler shift when the satellite is observed at the zenith. Interesting thing, this is on the Doppler shift concept. So, let us see this. In same much more. So, here you see, if this is the Earth and so let this is the radar and the satellite. Now, horizon, what is called horizon? If you look from the horizontal direction, the point where you are seeing the satellite. So, that means the satellite is here. So, let me use some other color. This is the satellite. Okay. Now, the question is, what is the direction of the satellite's velocity? You see, if it is here, so satellite is this, radar is this. So, radar is looking here. This velocity vector is perpendicular to this. So, what will be the Doppler shift? Doppler shift will be 0. So, this is at the horizon. Now, the question is second part. So, this was the first part, this is the horizon part. So, there will be no Doppler shift. Please remember this thing, that it appears that there may be some shift etcetera, but the two vectors, they are perpendicular. The range vector, this is the range vector, this is the velocity vector. So, their projection on this will always be 0, that is why no shift. The second part is that okay, you have the same problem, radar. Now, the satellite is at the zenith. Zenith means at the top, that means just on top of your head. So, this is the satellite. Again, what is its velocity? Its velocity is this, and this time what is the radar range direction? This. Again, you see these two are perpendicular. So, always you will see that these two are at perpendicular, that is why here also no shift. Remember this. Okay. So, next problem, what frequency will result in the maximum radar cross section of a metallic sphere whose diameter is 1 meter. So, what frequency will result in the maximum radar cross section of a metallic sphere whose diameter is 1 meter. So, you have a metallic sphere. Now, at what frequency? Because we have seen that graph, the how a sphere's RCS varies with the radius of the sphere. So, based on that you will have to answer this. Similarly, in the part 2, at what frequency will the radar cross section of a ball bearing whose diameter is 1 millimeter will be maximum. The two ways of saying, so that means same thing, but you see one is a 1 meter diameter metal, another is 1 millimeter metal. So, just to give you an idea what is the frequency there. So, what I will call this is problem, two problems, 1, 2, so third problem, let us say. So, here we can say the in part 1 RCS of a sphere, metallic sphere is maximum, RCS of a sphere is maximum. You can see that graph we have discussed in the class when 2 pi a by lambda is 1. So, here it is given that 2a is 1 meter. So, we can say that lambda will be pi meter, and so lambda pi, now I will have to convert it to frequency. So, frequency is c by lambda. So, that means c is 3 into 10 to the power 8 and lambda is pi, pi is value pi. So, that will give me 95.49 megahertz. So, that means if I have a 1 meter diameter thing at 95 megahertz roughly, it will be very good. That means, if you want to observe a 1 meter diameter something, so frequency you should choose if all other things are not considered. Just from choosing frequency, you will choose a VHF type of radar. Now, the same thing I want to observe now a ball bearing of 1 millimeter. So, here only change will be that 2a is 1 millimeter. So, now rest of the thing you do, and so f will be 95.49 gigahertz. So, this is an important thing, that you see that roughly the smaller I want to observe, I will have to go high in frequency. Suppose rain, generally normal radars like UHF radar or microwave radars, rain do not affect them much. But if I want to observe rain, I said also in the class that you will have to scale up the frequency. So, if I want to observe rain, if I want to observe weather, I will have to go high in frequency. So, that then the RCS of the thing becomes same. So, this is also an important lesson. Next problem, let us go. So, this one we have done, then 3 variants. Acha. So, I will have to give you those formulas. Actually, we will show you in the books, etc. If you just manipulate, there are 3 radar range equations are given. Out of that, one will be does not contain explicit indication of wavelength. In equation B, the wavelength is in the numerator, and in equation C, it is in the denominator. How do you respond to the question? How does the radar range vary with the radar wavelength, everything else being the same? So, what I will do, let me call this 4. No? So, and I will give you that you can see in the books the R max, you can write it as PT GT A sigma by 4 pi whole square S mean 1 by 4. Let me call this one equation A. Also, if I just make this AE put its value in terms of GT, I can also write this as PT GT square lambda square sigma by 4 pi whole cube S mean whole to the power 1 by 4. On the other hand, if I eliminate GT, that means put this GT in terms of AE, you see from this equation is both GT and AE are present. Now, in sometimes we make that okay, if GT is known, we can convert AE to GT or GT to AE, we know that conversion. So, if we write it in terms of AE, then the equation becomes PT AE square sigma by 4 pi lambda square S mean whole to the power 1/4. Now, interesting thing is you see that in the first equation the lambda is not present explicitly. In the second equation lambda is in the numerator. In the third equation lambda is in the denominator. So, the question is how does the radar range vary? This is the range, how radar range vary with lambda. So, you see you can all do these three things by remembering that what is AE? AE is GT lambda square by 4 pi. So, actually AE and GT are related. So, by that these are the three variations. Now, the question is then what is the actual dependence? So, what we will do, we will solve this. So, if we start from equation A, we can write that R max is PT GT. So, we are putting the value of AE GT square lambda square by 4 pi sigma by 4 pi whole square S mean to the power 1/4. So, this will become PT GT square lambda square sigma by 4 pi whole cube S mean whole to the power 1 by 4, which is nothing but equation B. So, starting from A we can go to B, and again from starting from equation C we can say that R max is equal to PT GT square lambda fourth by 4 pi square sigma by 4 pi lambda square S mean whole to the power 1/4 is PT GT square 4 pi whole cube S mean 1/4, which is again your equation B. So, equation B is the one you see PT doesn't have any lambda dependence, GT also once an antenna is there it doesn't have any dependence. So, basically we can say that all equations are same, and so R max that's varies with lambda to the power half. You see lambda square 1/4, so it is square root proportional to lambda. So, that is the main thing. That means, if you scale up lambda in a square root fashion, the R max will scale up. So, that was the third problem. I think time is up. So, we have seen enough problems on these basic concepts, that what is RCS, this radar range equation, various thing. Always remember in this last problem that actually AE, this is a electrical concept. AE is electrical concept, that is why the lambda is directly affecting this effective area. It is known from antenna theory, etc. So, do not think that effective area is of an antenna is independent of lambda. It is highly dependent on lambda, and that is why you are getting all these apparent anomalies, but actually there is no anomaly. The radar range that varies as a square root of lambda. Okay. So, thank you. From next day we will start the CW radar. Thank you.